Hi, so today we're going to move on to deriving heat diffusion equations for spherical coordinate. So for spherical coordinate, it's going to be a little different from radial coordinate. So instead of and as well as Cartesian, so X, Y, Z for Cartesian, and then we have theta, Z, and radius for radial, and then we have theta, phi, and radius for spherical. And let's draw it out, okay? So first, we're gonna draw the regular XYZ coordinate. And then we have X, the R, okay? And then the extension of it would be dr. And then we have the angle theta here. And then we would have uh an angle over here, and that's angle phi, and then we're gonna draw this, okay? It's so we're gonna draw a spherical figure in its mirror. Let me just redo this actually. This one be d theta, and then we would have this, 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 and then so we would have heat flows in three direction. The first direction would be um the direction would be the radius direction that goes through here. And then we have um heat flow through the theta direction. The and then we have phi direction. And then so first we're gonna define our control volume, okay? Radius is already in unit length. And then so of the problem that we have done before, we know that the to convert theta to unit length, we times it by the radius because theta is in radian. And then for phi, it's a little tricky, okay? So let's just draw this. I'm gonna help you guys figure this out. And let's see, we have an angle theta right here, and then this is the radius. So we want to find the radius, the arc length created by angle phi. So we need to know its radius. So if you look at this, this is the theta direction, okay? And then we know, and we know that the phi direction goes like this. So we would have kind of like shape up like this. So this is this curve over here is expanded by theta by phi. So the radius of phi would be this, and you see that this isn't it just radius times sine theta, because look at it, sine theta is equal to the opposite times radius, which is hypotenuse. So opposite is this line. So we're gonna have um unit length for phi would be r sine theta times d phi. As you times, oops, let's go back to this. As you find, this is the radius and then angle. So we have arc length. So our control volume would be dr and then d theta r and then d phi r sine theta. And so now we're gonna start writing our energy balance. Okay. Energy balance equation. So we have energy storage, and that would be equal to density times heat capacity times change in temperature with respect to times the control volume dV. I'm just gonna write it out. So dr times d theta r times d phi r sine theta, and then energy generated would be Q times the control volume. So I'm just gonna copy paste down here. And then now we're gonna work through for every single direction for the net heat flow, okay? So net heat flow, oops. So for R, direction of R, we have Q R E plus dr is equal to Q R plus D temperature times dqr times dr with R equal to R1. So we're gonna have and then times dr. So using our in minus out equal 0 for steady state or just any accumulation, we would have the Q net for R is equal to negative delta QR over dr times dr. So this would be uh negative dr times negative K times area um times dt over dr. Negative cancel out. So area for R would be this surface right here. And that's just the unit length of the other two coordinates. So we would have R d theta times d phi r sine theta. And then so we know that R is a variable, so we keep it in the bracket. So we have d dr times k kr squared dt dr times dr d theta d phi and sine theta. And then we move on to q net for theta. That would be negative q theta over d theta is equal to negative d theta negative k. So area would be dr times r sine theta d phi time. So like we said before, temperature gradients goes with distance, so gotta convert theta into arc length. So therefore we would have 1 over r dt dr over dr. And then we dt d theta, I mean, sorry. And then we take r and d theta out. We would have d theta k sine theta dt over d theta, and then r we also cancel out too. So we would have dr over here is d theta. Sorry for the confusion. So we have dr, d phi, and d theta. And then q net for phi would be negative q phi d phi. D phi is equal to derivative of d phi with respect to d phi negative k, and then the area that d phi penetrates through d phi direction would be r d theta times dr over, and then for the temperature gradients of dr, that would be we gotta convert it to arc length, so dt ds and dt over d 2 pi with r sine theta d phi times phi. So we would have 1 over r sine theta dt over d phi times d phi. So we take all the constant out and then cancel out the negative sign. We have k over dt d phi, or dt d phi, and then the constant would be r do d phi and dr, and then over 1 r sine square or sine theta. And then now we're gonna write all of our energy balance here. So first we have the energy storage, which I'm gonna copy paste it here. And then we have the energy generated. And then plus all of the net heat flow. I'm just gonna copy it all over here. So we need to divide it all by the constant volume. And so over here we see that this all of these terms are missing an R to complete missing two R to complete the volume. So we can add it R square over here and then times 1 over R square. So we can cancel this out. And then for here we would apply the same thing. So we would add R square sine theta and then times R square sine theta. So we can cancel this. And then over here, um, we are missing 2R. So I need to times it by sine square theta times R square. And then divided by R square sine square theta. And then we can cross out this. So we would have dt over change in temperature with time is equal to Q over PC plus A. So like K over density, heat capacity is equal to derivative of dr, R square, um, dt dr, um, times 1 over R square. plus um d d theta times sine over, smooth it down here, sine dt d theta times 1 over r square sine theta plus d theta times d phi. Oh, we can actually make this a second derivative. So d square temperature over second derivative temperature change with respect to phi times 1 over r squared sine theta. So yeah, that is it, guys. So this is the heat diffusion expression for spherical coordinates. And then now I'm gonna simplify it with no heat generation, steady state with only radial direction. And we're gonna find the thermal resistance, okay? So we have energy storage is equal to 0, and energy gen is equal to 0, and no phi or theta direction. So only we would have from our energy balance equation, we would have alpha times d over dr r squared dt dr times 1 over r squared. And 1 over r squared is a constant because it's outside the derivative. So we can cancel out both of this to get d over dr, r squared dt dr is equal to constant, is equal to 0. So therefore r squared dt dr is a constant. And then now let's compute a constant, okay? So let's find what that constant is. So dt dr is equal to c constant over r squared. We do separation of variables. We have c over r squared times dr. Integrate both sides. We would have delta t is equal to, let's do the set up the boundary for let's see what the question was. Let's do inner radius and outer radius, okay? So Ti, To, Ri, RRO, Ri, To, Ti. So delta T would be constant over 1 over R. Yeah, so for that's the derivative that we just found. I'm just gonna rewrite this like this. 1 over R1, Ri minus 1 over RO. So C is equal to um delta T times 1 over R1 minus 1 over RO. Okay, and then so now let's let's apply Fourier's law, okay? For heat conduction. So K Fourier's law is Q over K A dt dr. Negative K, so negative A is 4 pi. So we're trying to find the outer area of the circle. So we would do 4 pi r 4 pi r square um times dt dr. We just figure out that dt dr is equal to c over r squared, and c is dt times 1 over r1 ri minus 1 over ro um times 1 over r squared. And so Now let's do a circuit analogy, okay? So we have delta V is equal to IR, and then for thermal, we would have delta T is equal to Q times the resistance. So we have delta T here and we have Q here. So the rest of this would be our resistance. So let's write it in the correct term, okay? So R, we would have R square is equal to negative R squared is equal to K 4 pi R squared. So cancel R squared out, we would have 1 over 4 pi K. 4 pi K would be the resistance. So therefore delta T, for this delta T is equal to Q times negative Q times 4 pi and K. 4 pi K times I'm sorry, I forgot this part as well. So let's redo this. So we'd have R total would be 1 R square over negative R square over K 4 pi R square and 1 over RI minus 1 over RO. R square cancel out. So we would have minus negative 1 over 4 pi K 1 over RI minus 1 over RO. And that's our total resistance.